Today's roundtable that we're having with Airbus,
Cailabs and Cosylab, and we will be addressing an increasingly important domain of optical or laser communications between ground and space. We will be looking at the very basic, starting with the very basics. We'll look what are the challenges, what are the benefits, and we will also look what are the market trends and what the future is bringing for us. But before we go on, let me introduce the panelists and their companies. And I will start on your left with Mr. Daniel Hendricks. Daniel is a business development manager and an aerospace engineering graduate from the Delft University of Technology. And he joined Airbus in 2007 and has been involved in launcher structures, solar arrays, satellite platforms, thermal hardware, and since 2019, he's been responsible for business development on laser communications. And I think that Daniel's employer is so well known that I don't need to represent Airbus specifically. Next, Mr. Olivier Jacques Sermet is joining us from Cailabs, a French company based in Rennes. And Olivier is an optical engineer by training and has spent more than 15 years in deep tech, innovative photonics companies, transitioning from R&D positions into international customer support, sales, and business development roles. He joined Cailabs in 2020 to manage sales and business development of the fast-growing Tilba product line dedicated to laser communication. And as you already figured out, Cailabs is a deep tech company, an expert in light shaping solutions based on the patented MPLC technology. And in the field of free space laser communication, Cailabs develops ground segment solutions from core turbulence compensation components to optical ground stations. Last but not least, we have Miha Vitorovic and Harshraj Raji with us from Cosylab. Miha is a computer science graduate and is leading the space development department at Cosylab. And Harshraj is a mechanical and space engineer, and he has been working as a mission analyst and a system engineer on various industrial and space missions. Just briefly about Cosylab, we are a provider of control system software solutions in various domains, including space, and our expertise lies in the ground segment, in mission control systems, onboard testing software, facilities, telescopes, and much, much more. So just feel free to drop by our booth and we'll explain more. So without further ado, let's start. And to open the discussion, let's briefly introduce laser communications in the space domain. So what are the main characteristics, the benefits perhaps? Raj, would you like to take this?
Yeah, thanks, Tadej. Hi, everyone. So yeah, basically laser communications modulates carrier waves, which are the upper end of the infrared portion of the electromagnetic spectrum. This means much shorter wavelengths, right, as compared to radio frequencies. And shorter wavelength means two things. Shorter wavelength, you pack data onto tighter waves, right, which means a much higher bandwidth as compared to radio frequencies, allowing for more data to be transmitted over a single link. A shorter wavelength also means very narrow beam divergences, right?
Yeah.
This reduced beam spread means increase in intensity of the received power, of course, for a fixed transmitter power. Also, because of the high directionality of optical links, they are less prone to interception, jamming, and eavesdropping, thereby making them inherently more secure, right? Also, as we know, the radio frequency spectrum is getting increasingly congested, right? Because it's constantly under attack by well-resourced terrestrial applications, but also a number of people in the space sector. You know, this demand is increasing. That's why the RF spectrum licensing has to be overseen by some authorities, like the International Telecommunications Union, for example, right? Compare this with laser communications, and where this is not the case yet. You don't need spectrum licensing yet. Mm-hmm. So this translates to significant reduction, right, in initial setup cost and time.
Thank you, Raj. Thank you, Raj. So all those benefits, it sounded great, but this is a relatively new domain, and there must be also some challenges to it, not just technical, but also environmental and the other ones. And perhaps, Miha, would you take this?
Yeah, thank you today. Hello, everyone. So yeah, there are quite a lot of challenges they have to do. I mean, in space, we have been able to establish communication over several million of kilometers, but on Earth, you know, we're struggling to get a high-speed communication over a couple of kilometers. And there are many reasons for that, you know, like rain, fog, weather in general, background noise, scintillation. And we can offset some of those. For example, for the background noise and and pollution, we can maybe put the ground station into remote areas. But then there are different challenges there. How to get the ground stations to those areas, you know, most of them have to do with logistics. How to get enough high-speed data connectivity to them, how to power them, and obviously how to get maintenance crews there when it's needed, because, you know, they can be up on some mountaintop or something. But even if we put them on some remote locations, you know, the cloud cover can go over quite a large area. So then this we need to mitigate in some other ways, maybe by having a network of optical ground stations over a very large area, or by having a radio frequency fallback.
Thank you, thank you. So perhaps if you go more to a high-level discussion, Daniel, as a business insider, can you give us a brief overview of the state-of-the-art in free space optical, or will it actually ever replace RF communication?
Thank you, Tadej. It's a very good question. So let's first go to the last question, which is a very relevant one. The answer is no. We don't see that optical will ever replace fully RF. It's a misconception to ever think that. Yes, it is the future. Yes, we believe you will need it, because RF won't be sufficient anymore at some point. We don't know exactly when that is, so we follow the market, we follow our customers, and of course we try to create end-to-end solutions. I work in a portion of Airbus where we focus on the ground segment and aerial terminals, but all this needs to work together, and only when we find a solution that actually fits the market needs, that's when we will be ready for it.
Thank you, thank you. So we are looking at a hybrid model in the foreseeable future, but with an increasingly important role in optical. So perhaps, Olivier, why do you think that the time for optical is now? Why is it a good moment?
Thank you, Terry, for this relevant question. I would be a bit bolder than Daniel here by thinking that the future is already here, is already now, and we are. I think we are in an inflection point for free space optical communication now, thanks to the alignment of 3 planets. We have overcome some technical limitations. We'll go through them a bit later with Raj. And we've really overcome many things, including atmospheric turbulence, which is a very hard one to tackle. We are seeing the emergence of use cases from Earth observation that requires super large chunks of data brought back to Earth, to telecommunications and more sovereign and defense applications. And third, we have a solid stream of VC money to fund these infrastructures. So right now is the right timing for LaserCom.
Mm-hmm. Thank you, thank you. So talking about this infrastructure, let's look perhaps a little bit more closely. What does an OGS, optical ground station, actually consist of? What subsystems are included? Raj would...
Yeah, sure. Thanks, Tadej. So what an OGS basically has to do is collect the photons with a telescope and focus them onto a detector, right, where the light is converted to electrical signals, which are then further processed to recover the information actually embedded in the laser beam, right? But an OGS is much more than just the telescope and detector. Because of the fine pointing requirements of this technology, you need a dedicated pointing acquisition and tracking subsystem, right, which consists of sensors and electronics which steer and control in closed loop the active elements of the optical bench assembly, so fast steering mirrors. Then you also need a subsystem to monitor and control the parameters of your transmitted laser, right? And of course, you need to characterize the signals, both for the received as well as for the transmitted beam, which is why you need a dedicated subsystem for that. In addition, your OGS also has to interface with various external systems. Since, as Mia was mentioning, you know, this technology is highly weather dependent, right? So you need to talk to a meteorological station or weather station, of course. Yeah. Also, your OGS needs to have good knowledge, let's say, of the orbital elements and trajectory of your target satellite, which is why it needs to interface with a mission planning system or a satellite control center. Yep. Of course, if your OGS is part of a network, it also needs to be hooked up to a network subsystem, right? So all the ground stations in the network can see and talk to each other. Yeah, and yes, I'm also aware that quite some work is being done on systems which are meant to mitigate the effects of atmospheric turbulence.
So talking about atmospheric turbulence, Olivier, this is probably your field. Can you explain how are we able to challenge that issue?
Yeah, you're right. This is one of Cailabs' specialties. So let me explain a bit more. The effect of atmospheric turbulence is to actually scramble the signal that comes from the satellite to Earth and to completely disturb the optical signal. So what you need to do is analyze these disturbance and correct it before actually having a usable telecom signal. So the effect can be scintillation will scramble it. There will be defocus, distortion, tilt, and everything. So you need to have very complex and fast systems to deal with it. So some historical solutions using adaptive optics, which works well, comes from the imaging telescope world. So this is one way of dealing with it, by analyzing the phase of the signal and correcting with deformable mirrors. And now we have new, more innovative solutions based on spatial demultiplexers and optical recombiners that are able to do this in an all integrated way.
Thank you. So perhaps the next question for Micha. We heard that there are multiple subsystems and there must be some capable software needed in the background running all this complexity and making it work.
Yeah, thank you. Yeah, we see software connected to the optical ground stations. You know, it has two major dimensions. One of them is obviously transferring the data between the optical ground stations to where it's needed, and the other one is basically integrating all the different subsystems that you mentioned here to work as a single device. So there will be many different devices and subsystems that work here, and you need to connect them together. And this is basically exactly what we've been doing in our past projects for the last 20 years. You know, we see many similarities here. One of them is obviously, like I said, connecting and integrating different subsystems and sometimes exotic devices into one working system. Then obviously making sure of the very stringent and requirements on the reliability and the data transfer. Obviously you want to have a robust system with as little downtime as possible. Sorry, because downtime costs money. And obviously, we see things here like automated FD or something that enables you to minimize human intervention that is needed sometimes because the systems are in a dangerous environment. This is where we've seen them in the past projects, but here basically, like I said, they will be in remote locations often, so it would be quite expensive to get maintenance crew there.
Thank you. So definitely a lot of complexity, but also possibly also fragility. And how do you mitigate that to ensure uptime? Does software play a certain, let's say, an important role here? How can it help? Perhaps a question for Daniel.
Well, thanks again. Yes, indeed. We hear the words complexity and all these different technologies. We, of course, understand very much these are all needed. And we see these things as indispensable to be in place. They need to be developed. We see them in various stages of development. I think Olivier is right to be very optimistic about the state of affairs. Yes, you could introduce optical comms in many levels already. But we do see if you're going to a larger scale introduction, which is exactly what Airbus wants to promote and of course wants to be in the lead, and I should say stay in the lead, because Airbus has been of course paving the field already with EDRS, the Space Data Highway, getting the first optical intersatellite linking in place. Now it's also on us, we feel, it's our responsibility to use that heritage, to use that credibility, to sustainably and commercially attractive get this technology literally assembled into either parts of other systems. So we want to partner with the cloud services providers, their end customers. There's various ways in which we can interact with customers on different levels. So this is especially what we want to do. And also happy very much that we can be here today to showcase that we're talking to partners like Cailabs and Cosylab, because we understand that the technologies that these companies have and that they're developing is indispensable for what we want to achieve. Airbus does not have the intention to develop everything ourselves. And so we need partners like this, and I think we should be very happy with ESA having promoted this project that we're in together. So,
thank you, thank you. So the technology will ensure the reliability and uptime, but what needs to be done to get free space optical communication to a broader use, large-scale use?
we need to limit cost. If you see it nowadays, if you want to implement optical comms, it will be still relatively expensive compared to RF, which can still do pretty much the same thing. So you'll be looking at what do different types of customers want at different stages. And an important thing I forgot to mention earlier when you talked about RF, some customers, and you can guess in which field, they would very much like to be discreet. They would not want you to know that they're actually communicating. If you only think about some of the earlier pictures we saw 2 weeks ago from Ukraine, those are pictures of destroyed radar stations. Those are just radio beacons. That's the first thing you aim for. Certain customers therefore want to be discreet. They want to know that they can send something without somebody sensing that they're doing it. For them, bandwidth or the other like licensing is not relevant, but being discreet is very much important. But still, cost is key to any customer.
Thank you, thank you. So perhaps the same or similar question to Raj, but from a more technical perspective. What do you think?
Well, I think the technology needs to be proven, obviously, and rendered cost-effective, both for the space and ground segment. Right. Thanks to projects like AlphaSat and the European Data Relay System, we do have some hands-on operational experience with optical inter-satellite links, but for space-to-ground, there's still quite little, which is why I think technologies such as adaptive optics or alternatives, signal encoding schemes, fast control algorithms should be further researched, developed, and de-risked. And by the way, ESA is offering a good opportunity for this with the future OPSAT-2 mission. Right, because the theme of OPSAT-2 is optical communication, right? Yes. Also, I think a collaborative approach should be adopted between members of the supply chain, right? And lessons learned should feed back into the design and refinement of operational concepts of such systems. This is why, as Daniel mentioned, this is why Cosylab and Airbus are collaborating on this project together, and this is why ESA is supporting this development. Yeah.
Okay, thank you. Olivier, what are your thoughts about bringing this technology into our everyday lives?
I think I fully agree with what my colleagues have just said, and really one of the keys to go from a neat technology niche to actual business cases and real economic equation for laser comm is to get all the supply chain ready, to get everybody to have everybody scale up from prototyping to production, and all this doing in good intelligence between the SMEs, startup companies, new space companies, and the big primes, all of these working together. So I see there are a lot of nice projects, ESA project between Cosylab and Airbus. We're involved in such projects. We announced the Cailabs project to also demonstrate some links between space to ground. So all these demonstration projects are part of this scaling up, demonstrating the use cases, and then scaling up together to mass production.
Thank you, thank you. So let's switch to the next topic. So let's talk about the future. What are the main trends? What's in it in the future for us? What are the main trends that will play a significant role in the future? Daniel, you've been in this business long enough. What's your take on this?
With thanks to my colleagues, of course. Well, if you look at it, we see the way in which we feel optical comms will be adopted a bit sooner than we had anticipated. You see an interest in quantum key distribution, for which optical communication has a very inherited advantage. There's something about quantum, and I'm not an expert on quantum, but I still need to meet one who can actually explain to me all the details about quantum, which probably sounds familiar. But the inherent advantages of the ability to distribute keys like we do with optical comms, that's something that only laser communication can do. So this is where we see already the market picking up. I think the next level will be, at least that's what we're preparing for, is the direct-to-earth constellation market. If you look at what's now going on, Starlink having inter-satellite linking, Airbus already doing it with the Copernicus program in EDRS. The Space Development Agency in the United States, they're looking at all inter-satellite linking. The next step for that, and that's all low Earth orbit, is to get that data down to Earth directly. So we think that's the next market to actually pick up. In a couple of years, perhaps say 5 to 10 years, we'll probably see that the capacity issues, the licensing issues, also for geo optical feeder linking, will become interesting enough for laser to make a difference there, where the actual RF type of ground stations will no longer be sufficient. This also ties in with the fact that the market will be different. The whole concept of optical is of course different, so there will be a new business model of where to place these stations, how to interconnect with them, who takes care of that infrastructure. All that still needs to be developed. So we're talking, of course, to all sorts of customers and parties who need to be in that, but the traditional parties are also looking how to deal with that. RF is just inherently a different business model. Then when I think we've established what the place will be for geo to earth and ground to geo, that's when I also think we'll see a change in aerial airborne terminals, which is still now something which we think might be going on in defense markets, but then quite specifically. But if you think about it, who's willing to pay enough euros on a regular aircraft to have Wi-Fi? It's just something you expect, like in a hotel. So we find it very difficult to see a very big commercial market for airborne connectivity using lasers in the short term. So that would be the order if you ask us.
So how does actually Airbus actively respond or actually create those trends?
Honestly, by carefully assessing what's happening. Of course, we have a lot of feelers into the market, and we want to be very careful about how we approach it. You can shout off the rooftops what you intend to do, the make it or fake it approach. I feel we can't do that. It's not the type of company we are. So we carefully prepare. We carefully follow what our customers and intended customers want to achieve. And we want to be ready when the time comes, and we will be.
Thank you. We were discussing with Micha previously about how Cosylab would be in the supporting role here, so perhaps.
Yeah, we definitely see us supporting you there in a technological sense, you know, by providing software that can help you control those ground stations and all the distributed systems there. But also some of the activities that we've been involved with is the in Europe with ESA, with EGSCC, which is a new and modern ground system, common core that they are developing to be used by all the players in Europe for all the ground system need. And definitely one of those needs, I think, will be the optical ground stations.
Thank you, thank you. So I think that we have effectively and productively used our time with the panelists, and we wanted to leave some 5 minutes or so for the Q&A from the audience. So please feel free to ask anything that could be on your mind, and we'll try to answer it.
Hi, I'm Jeremy Giampoli with Northrop Grumman. I'm interested to hear what you think, you know, as we go from satellites that maybe have 1 gigabit per second up to 10 gigabit per second downlink up to, you know, a laser enabled maybe up to 100 gigabits per second, you know, raising 1 or 2 orders of magnitude above the data rates. Are there stressors on the infrastructure, you know, both at the ground site specific and maybe the ground site software, but as well as further downstream in processing and data storage, as you see, you know, this huge increase in data rate?
Daniel?
Who's taking this?
Yes. There is still a big challenge in that. I think your question is about where would the bottlenecks be and where would they remain. And I think that's true. And I don't think anybody has the right answer yet. This is what I'm saying, we're preparing carefully, because you don't want to box yourself into certain types of a solution that then no longer grant you any room to move. Fortunate thing is, of course, when you go to the ground segment, you can always fix it. We're used to launching stuff and then it's goodbye. But you're right. I don't have an answer specifically on how we should deal with it. But I just consider it one of the remaining challenges. Anyone else wants to comment on that?
Just a very short comment on that. Going from 10 gigabit per second to hundreds requires a change of technology optically. You have to go to coherent detection, and that creates challenges both in space on the type of the lasers and components you have to put there, and on the reception. And this is where turbulence and all these effects that we mentioned become really, really problematic. And we're tackling them, but they're still, like, today putting 100 gig in space is like the size of 2 washing machines. So we need to bring that down before it becomes like broadly used.
Thank you.
Watch that space, because next year Airbus will be launching Butter 8 with the Telio system on it. That's right. Watch it.
Thanks. Any other questions? Gentleman here.
Thank you. Hello. Just about the environmental aspect, I heard before that there is some things to be assessed, but I understand that optical communications with laser are much less impactful than RF frequencies. Is it correct? In terms of biological effects?
I don't know what RF does to ecological.
Yeah, let's say the impact of radio frequencies with what we use today, no, for RF communications. So, with respect to laser communications, when you go from the space to the ground.
I honestly have no idea how to answer that.
Okay.
Sorry.
No problem.
Anybody want to try?
Biological effects.
So, Johnson, what are your question when you mentioned the impact of the waves on biological life or compared to lasers? Or?
Yeah, for biological effects, we know, for instance, for the telecommunications, the spectrum from up to 26 gigahertz as something that needs to be assessed. I imagine, we know also that light technologies have a lower...
Okay, I understand the question. I don't think I can comment on the RF spectrum, because I think there are a lot of studies on that, and it really depends on many factors, wavelength, how close you are to the source and everything. What is sure is that the laser comm first is highly directive, so it really limits the impact to a very thin line. It's really point to point. And second, the standards and the way it's designed is really meant to be eye safe. So using wavelengths that are not harmful to animals or human eyes, of course, except if you put your eye right in the laser, but it's really designed to be unharmful to aircraft also, because you don't want to blind the pilots. So, and there are different standards, CCSDS, SDA, and others, which really are tackling this to make sure that laser comm doesn't bring new sources of harm. So I don't know if it's better or worse than RF. I can't comment on that, but what I can say is that it's taken into account in the standards and by the industry.
One final question, otherwise we're done. So thank you again for joining us. Thanks to all the panelists for the interesting discussion, roundtable, and feel free to meet us at our booth. Thank you.
Thank you, everyone.